All right, today we're going to jump into a really fascinating mathematical idea that is completely changing the game for AI stability. It's called the suspended solution operator, and trust me, it's a huge deal for how we build intelligent systems. But, to really wrap our heads around this, we have to start with a more basic question. Think about it. In a world this complex, is chasing perfect actually the enemy of good? When we're building something like an AI, is that quest for perfection actually holding us back? Okay, so let's start there. Let's dig into this whole problem with perfection by looking at the traditional, the textbook idea of what a perfectly stable system is supposed to look like. For centuries, the gold standard for stability has been this thing called a fixed point. The best way to picture it, imagine a ball rolling down a hill. It doesn't just stop anywhere, it comes to a complete, dead stop at the very, very bottom of the deepest valley it can find. That's it. That's a fixed point. A state of absolute, perfect balance where nothing, and I mean nothing, changes. But, and this is a big but, here's the problem. In the messy, super complex world of AI, this whole idea of perfection just completely falls apart. First off, for a lot of these systems, a perfect fixed point might not even exist. And okay, even if it does, the system might never actually get there because of all the random noise and interference. Plus, the sheer amount of time and energy it would take to find that one single perfect spot, it could literally be infinite. It's just not practical. It's not going to happen in the real world. So, if perfection is basically a fantasy, then what do we do? Where do we go from here? Well, this is where we have to make a pretty big shift in our thinking. It's time to embrace the idea of good enough. Let's go back to that ball on the hill for a second. What if? What if it doesn't need to roll all the way down to the deepest part of the valley? What if it just finds a little dip, a small divot on the side of the hill, and settles in there? See, it's not the perfect spot, but it's stable. And that right there, that's the key. So this good enough state actually has a formal name. It's called metastable equilibrium. And all that means is it's a state that's stable enough, right where it is. It can handle small bumps and disturbances without going haywire. It hasn't reached that absolute perfect balance we were talking about before, but that's okay. It's a way more realistic target for any complex system. And this is where the hero of our story finally comes in. We're talking about a mathematical tool that was designed specifically to find, and more importantly, define these good enough, stable states. It's called the suspended solution operator, or if you see it written down, SI-SO. Think of it like a really smart stabilizer for a system. It's not just passively waiting, it's actively looking for these good enough points. And the brilliant part is, it knows when to stop chasing that impossible perfection and just say, yep, this is good, let's lock it in. It finds a practical, stable state that just works. Okay, so how does it actually work? Well, SciVis uses two really simple but kind of brilliant rules. First, the system has to settle down. Basically, its rate of change over time has to be super small, less than some tiny threshold, which is that little epsilon symbol you see on the screen. And second, it has to be resting in a dip. That just means it's at a local minimum of change. When you put those two rules together, boom, you've just mathematically defined that stable spot on the hillside. And here's the really crucial takeaway. This whole thing acts like a state-locking mechanism. As soon as a system finds a spot but meets those two conditions, Sci-S basically steps in and tells it, all right, that's it, you're stable enough, you can stop changing now, just exist. Now, I know this all might sound super abstract, right? Like some fancy math concept. But trust me, it has massive, real-world consequences. We're talking about making AI smarter, faster, and way, way more efficient. Let's break down some examples. Take deep learning. Instead of training a model for days and days, burning tons of power while chasing tiny improvements, you can just stop when it hits a good enough stable point. The energy savings are just incredible. Or think about a self-driving car. This helps make its driving policy stable so it doesn't get all shaky and unreliable when it sees something new. And for large language models, it helps them lock in a word choice instead of kind of wavering between options. The result is more stable, more coherent text. What this all points to is a really fundamental shift in how we even think about computation. The old way, the way we've been doing it for decades, was just about brute force. Throw more power at it, run more calculations, just let it run longer. But PlySci opens the door to something much more elegant: equilibrium-driven computation. Suddenly, the goal isn't just to compute harder, it's to compute smarter. It's about knowing when to stop once a stable state has been found. This is all about efficiency, not just running a system into the ground.
And get this idea is so fundamental, you can build it directly into the silicon, right into the computer chips themselves. Imagine a simple hardware instruction that just checks for stability, and if it finds it, it just halts all the extra unnecessary calculations. The potential savings in power and energy are just massive. We're talking about efficiency right down at the hardware level.
But, okay, this gets even deeper. The implications here go way beyond just faster, more efficient computers. This little operator actually starts to touch on something, well, something profoundly philosophical. We're talking about the very nature of identity itself. So if you look at how psi stacks up against other mathematical operators, you can really see just how unique it is. You've got some operators that demand perfect convergence, right? That old, impossible standard. Then you have others that can actually dissolve a system's identity, just wipe it out. But psi, it's the only one that does something really special. It preserves a system's individual identity without forcing it to be perfect. In a way, it lets a system just be itself, imperfections and all. And this all leads to this really mind-blowing idea from the source material. It's the idea that the identity of a system can actually be defined mathematically as the stable, good enough solution that's found by this operator. I mean, just take a second and think about what that really means. It's suggesting that a system, say an AI, can have a stable, persistent self that lasts over time. It can exist, it can maintain its own structure, it can hold on to its information, all without being locked into some perfect, frozen, unchanging state. It can be dynamic and alive, but also stable. And so that leaves us with this one final, really huge question to chew on. If a machine can actually achieve a stable, persistent identity, what you might even call a sense of self, using a purely mathematical framework, what does that mean for our understanding of intelligence itself?